Good afternoon, everybody. My name is Ryan, and this afternoon I'm going to be talking about some work that I did as part of a group of the other people you can see on your screen, looking into the effects of UV aging on laser sintered nylon-12 parts. So I guess the first question really to ask is, why do we care? Why do we do this research? So we've seen an increased interest from industry in using polymer powder bed fusion for creating end-use parts. And while we have a lot of information on how the parts perform when they come straight out of the machine, there's quite limited information on how these parts actually perform in service. As for why UV, we know that UV degrades polymers, and there's a potential for end-use AM parts to be exposed to UV just being outside, examples being sort of in the automotive and aerospace industry. But moving on to what we actually did, we first made some nylon-12 test samples in laser sintering. We then artificially aged them before measuring changes in both the appearance and mechanical performance of the parts. And then we did a load of analysis using a load of different techniques to identify any corresponding changes in the chemistry or the structure of those parts. Now, in terms of the appearance of the parts, we started to see some yellowing after only 24 hours of UV exposure. UV vis spectroscopy showed that this was due to an increase in absorption of blue light that was giving us that yellowing. And then when we did XPS on these parts, we found an increasing number of carbonyl groups which absorbed that blue light, giving us the yellowing in colour. Moving on to mechanical performance, we saw the parts became embrittled after 168 hours of UV exposure. But as you can see from the graph on the right, there was no real change in stiffness, which implies a change at the surface only. So we theorised that this was due to a possible reduction in polymer chain mobility at the surface, leading to easier crack propagation and premature failure. So looking at the surface in a bit more detail, we used a technique called monoenergetic positron spectroscopy, where we fire positrons at the surface of the part and then measure how long they take to annihilate, and this gives us an indication of the free volume between the polymer chains. And what this showed us is that we were getting a decrease in free volume between our polymer chains as the UV exposure increased, down to at least 1.2 microns from the top surface of our parts. And then finally, we looked at changes in crystallinity in our parts using DSC. And what we found is that we had a change in the number and type of crystalline regions as UV exposure increased. But again, we only saw that change at the surface of the parts. So pulling all of this information together, we first have our exposure to the UV radiation. This causes new carbonyl groups to be formed, which absorb blue light, leading to the yellowing of the parts that we saw. They also cause changes to the crystal structure at the part surface via a reduction in the surface free volume between the polymer chains. This leads to a reduction in chain mobility at the part surface, giving us the embrittlement that we saw. And then this in turn leads to crack propagation and premature failure of our parts. So that's it.